Welcome to Lucid Mind Chemistry channel. In this video, I'll be solving Chemistry A-Levels Structured Questions, Paper 42 from May-June 2021. For question timestamps and other useful information, please visit video description. Question 1, Part A. An aqueous solution of chromium-3 contains the green complex ion. Part 1. Complete the electronic configuration of an isolated gaseous chromium-3 positive ion. Now from periodic table we can find out the atomic number of chromium. Chromium is 24. In neutral atom form, its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, then we have 3d and 4s. Now first electrons are filled in 4s, then in 3d. Now we have 18 electrons, 18 and 2, 20, plus 4, it becomes 24. Now we can see that 3d has 4 electrons, which is unstable form, as d orbital is more stable when it is half filled. It must have 5 electrons, so 1 electron will move from 4s to 3d and it will become 3d5, 4s1. So this is the electronic configuration of neutral chromium. Now when 3 electrons are lost, first electron is lost from 4s, so 1 from 4s and 2 from 3d will be lost. So we have 3d, 3 as remaining. Now we can write the electronic configuration. We have 1s2, then 2s2, 2p6, 3s2, 3p6, and then finally we have 3d, 3. Part 2. Define the term complex ion. This is complex ion in which central element or central metal, it is surrounded by ligands. Now we can write the definition. It is a molecule or ion which is formed by a central metal atom or ion surrounded by one or more ligands. Now ligands are actually making coordinate covalent bond with the central metal. Part B, we have chromium H2O6, 3 positive, aqueous. It shows similar chemical properties to cobalt H2O6, 2 positive. Samples of chromium H2O6 are reacted separately with either sodium hydroxide aqueous, hydrogen peroxide aqueous, or excess ammonia in aqueous form. Use this information and data booklet to suggest the formula of the chromium species formed. State the type of reaction taking place in each case. Now we can see that the reactions are similar to cobalt H2O6, so we have to write similar products as was the case with cobalt H2O6. Now with sodium hydroxide, cobalt H2O6, it formed chromium hydroxide in precipitation reaction. So similarly, this will also form chromium hydroxide. And this will be a precipitate. Type of reaction is precipitation. Now you can also write another product in which all ligands are present. We have 3 water molecules and 3 hydroxide ligands present. So you can write, instead of this, you can write CrOH3, H2O3. There will be no charge on this complex because OH is -1 and chromium is +3. So we have 3 OH negative which are balancing 3 positive ion. Second part is H2O2, hydrogen peroxide. It can react with chromium complex to form Cr2O7. Or you can also write Cr2O4. And the reaction is oxidation, or you can also write redox reaction. This is because the oxidation state of chromium in this is +6, +6, so it moves from +3 to +6, which is oxidation. In third one, we have excess of ammonia. Now ammonia, it can replace all water molecules, so it will form CrNH3 6 +3. And the type of reaction is called ligand substitution, because NH3 ligand, it replaces water ligand. Part C, CrH2O6 2 positive, and this complex are both complexes of chromium 2 and have different colors. Explain why the colors of these complexes are different. Now colors, it depends on the energy gaps between the d orbital splitting. So d orbital, it splits into xy, yz, xc. These are on the same energy level, and then we have dx square, y square, dz square. These are at higher energy level. So there is an energy difference between these two splitted d orbitals. So what happens, that due to electronic transitions, it shows colors. And this splitting or this change in energy or delta E, it depends on the type and number of ligands. So we have water ligands present in one, and we have other ligands that are present in this second complexes. So therefore the energy gaps will be different and colors will be different. So we can write the answer. Energy difference is different as energy gap between d orbitals is different. And now what will happen, that due to different energy difference, different frequency or different wavelength of light is absorbed. And therefore different complementary colors are seen. For D, the structure of this complex is shown. Ethanoate ions acts as ligands in this complex. The ethanoate ligand CH3CO2 negative is shown as this one. Number 1, water and ethanoate ions behave as different types of ligands in this complex. Suggest an explanation for this statement. We can find out the difference from this given diagram. We can see that this is ethanoate ligand and it is bonded with 2 coordinate covalent bonds with the chromium, while H2O ligand, it is just bonded with 1 coordinate covalent bond with chromium. So the ligand donating 2 electron pairs is called bidentate ligand, while the ligand attached with just 1 coordinate covalent bond is called monodentate ligand. So we can write the answer. Ethanoate ions are bidentate because they donate 2 lone pairs. We have 2 oxygen atoms and both oxygen atoms have lone pairs of electrons, so therefore they can make 2 coordinate covalent bonds. Second is the water. It is monodentate as it donates just 1 lone pair. Part 2, reduce the coordination number of chromium and geometry around each chromium atom in this structure. Now coordination number is actually the number of coordinate covalent bonds that the central metal is making, and geometry depends on the coordination number. So in this structure we can see that we have chromium and it is making 1, 2, 3, 4, 5, 6 coordinate covalent bonds. So coordination number is 6. And for 6 coordination number, the geometry is octahedral. Part 3, state the type of bond between the two atoms in CR-CR bond. In the structure we can see that all bonds are coordinate covalent bond, whether it is between chromium and ligand or chromium and chromium. So we can write coordinate covalent bond or dative covalent. Then we have next part, part E. The complex reacts with aqueous acid to form Cr2 positive. Cr2 positive react with oxygen aqueous under acidic conditions. Cr3 positive ions are formed. Use the data booklet to answer the following questions. Number 1. Construct an ionic equation for the reaction of Cr2 positive with oxygen under acidic conditions. From data booklet we can find the equations. One is the reduction of chromium 3 positive, so Cr3 positive. It gains electron to form Cr2 positive. And the voltage associated is negative 0.41 volts. Second is oxygen under acidic conditions, which means oxygen with H positive, so we can also find the reduction equation for that one. Oxygen aqueous, it reacts with H positive and it also gains 4 electrons to form 2 water molecules. Now the voltage associated with this reaction is 1.23 volts. Now we can see that in one of the reaction, in reduction, the voltage is more positive as compared to the first reduction equation. So what will happen that this reduction equation, it will go in the forward direction because it is more positive. So more positive means reduction, while less positive will move in the backward direction and it will be oxidation. So now we can rewrite the first equation in reverse form. We have Cr2 positive. It goes back to Cr3 positive along with the loss of an electron. Now we can add these two equations together. First we should equalize the number of electrons. Now number of electrons gained is 4 electrons and number of electrons lost is just 1. So we can multiply this whole equation with 4 in order to balance the number of electrons lost and gained. So it will become 4 Cr2 positive. It converts to form 4 Cr3 positive along with loss of 4 electrons. Now we can add these two equations together and this will be the final equation. Now in final equation we have oxygen, O2, we have 4H positive, electrons lost and electrons gained are cancelled out. Then we have 4 Cr2 positive. Now the product is we have 2 water molecules and 4 Cr3 positive. This is the balanced ionic equation. Part 2, calculate E naught cell for the reaction in E part 1. For this reaction you have to find out the E naught cell. Now we can see the voltages. This one is more positive, so it is reduction. As E naught cell, it is equal to E reduction minus E oxidation. So this equation, it moves in forward direction as the voltage is more positive, so this is reduction, so we can write 1.23 volts. E oxidation, this one is oxidation equation. As this is less positive, so it will move in backward direction, so oxidation will take place and the voltage is negative 0.41. Putting in the equation, we can now find the E naught cell value. It comes equal to 1.64 volts. Question 2, part A, state and explain the trend observed in thermal stability of group 2 nitrates. Now, thermal stability of group 2 nitrates, it depends on two things. One is charge on cation and second is the polarizability of anion. As moving down in group 2, what happens that size of cation decreases. So we can say that charge density also decreases. When charge density decreases, the polarizing power also decreases. When polarizing power will decrease, so anion is less distorted or less polarized. So therefore it will become more stable. So down the group, the thermal stability of group 2 nitrates, it will increase. We can write the answer, thermal stability increases down the group. And the reasons are that the charge density of cation decreases. Group 2 cations, they can be represented with M and there is 2 positive charge on each cation. While the size it increases, so therefore charge density will decrease. So we can say that less polarization of nitrate ion will happen. Or you can also say that less weakening of nitrogen-oxygen bond. So nitrogen-oxygen bond will break less, so thermal stability will increase. Part B, part 1, lead 2 nitrate, we have PbNO3 decomposes on heating in a similar manner to group 2 nitrates. Write an equation for the decomposition of lead 2 nitrate. Now group 2 nitrates, they decompose to form three things. One is metal oxide, one is nitrogen dioxide and one is oxygen gas. Lead nitrate will be decomposed similarly, so we can write PbNO3 it will decompose to form lead oxide plus nitrogen dioxide plus oxygen. Pb is balanced. We have two nitrogen atoms, so we can write 2 with NO2. Now there are 6 oxygen atoms on the reactant side and 4, 5, 6, 7 oxygen atoms on the product side. So we can reduce one oxygen on the product by writing 1 by 2. Part 2 suggests how the ease of decomposition of lead nitrate would compare to that of barium nitrate. Explain your answer. You may find it useful to refer to the data booklet. Both are nitrates and different elements are there. One is lead and one is barium. From periodic table we can see that both barium and lead, they are present in period 6. Barium is in group 2 and lead is further in period 6. So what happens as we move along the periodic table from left to right, size decreases. This is because protons increase, electron increase and number of shells remain same. So moving from barium to lead, the size of lead will be smaller as compared to the size of barium. So when size decreases, charge density will increase. So we can say charge density increases. Now more charge density means more easy breaking of nitrogen-oxygen bond, because the polarizing power of cation will be increased. So therefore PbNO3, it will be less stable as compared to barium nitrate. So we can write lead nitrate will decompose easily. This is because the charge on lead or lead 2 positive has higher charge density due to smaller size. So it causes more polarization. Of nitrate. So that's why nitrate will decompose fast and it would be less thermally stable. C part 1, barium ethane dioate, we have BaC2O4. It decomposes on heating to produce barium oxide and a mixture of two different gases. Construct an equation for the decomposition of barium ethane dioate. Now we can write the formula. We have BaC2O4. According to the information given, it will decompose into barium oxide plus two gases are formed. Now we can see we have BaO, we also have carbon and oxygen. Now carbon and oxygen, they can make carbon monoxide, they can also make carbon dioxide, or simply oxygen gas can also be formed. So you can write any two from these three. You can write carbon monoxide with carbon dioxide, or carbon dioxide with oxygen, or carbon monoxide with oxygen. So I can write CO plus CO2. The equation is already balanced. Part 2, an impure sample of BaC2O4, mass is given 0.5 grams. It is added to 50 centimeter cube of 0.02 mole per decimeter cube acidified manganate, which is oxidizing agent, and in excess, a redox reaction takes place and all BaC2O4 reacts. The resulting solution containing unreacted acidified manganate is titrated with this iron 2 positive. The endpoint is reached when 30.4 centimeter cube of 0.05 mole per decimeter cube iron aqueous has been added. These are the equations. Calculate the percentage by mass of barium C2O4 in 0.5 grams impure sample. Show your working. Now from this we can understand that in the start we had BaC2O4 and it was impure sample. 0.5 grams. Now it is titrated with acidified MnO4 negative. Now this one is limiting and this one is excess. So all of BaC2O4 reacts while MnO4 negative is left unreacted because it is in excess. Then what happens is that they titrate this unreacted acidified MnO4 negative with iron 2 positive solution. So in second step we have MnO4 negative and iron 2 positive. Now we can find out the ratio between these two. From the equation given, we have this equation for iron and 1 electron is lost while 5 electrons are gained for MnO4 negative. So we can balance these two. Number of electrons lost must be equal to the number of electrons gained. So we can multiply this equation with 5. So it will become 5 Fe2 positive, 5 Fe3 positive and 5 electrons. Now electrons are balanced. So now from this we can find out the mole ratio. We have MnO4 negative, which is 1 mole, and we have iron 2 positive, which is now 5 moles. So we can write 1:5. Now from the given values, we have 30.4 centimeter cube of 0.05 mole per decimeter cube iron. We can find the number of moles. Number of moles is equal to concentration into volume. Concentration is 0.05. Volume is 30.40 divided by 1000, as we have to convert it into decimeter cube. So number of moles of Fe plus 2 comes equal to 1.52 exponential minus 3. So if 5 moles require 1 mole, then 1.52 exponential minus 3 moles will require x moles of MnO4. We can cross multiply to find out the number of moles of MnO4 reacting. So MnO4 negative moles, it is equal to, we have to multiply these two and divide by 5. Now number of MnO4 moles, it is equal to 3.04 exponential minus 4. Now these are the moles of MnO4 that have reacted with iron 2 positive. Now we can find the total number of moles present in excess. As in the question, they had given MnO4 negative in excess and it was 50 centimeter cube of 0.02 mole per decimeter cube. Now we can find the number of moles. Again, N is equal to C into V. So 0.02 into 50 divided by 1000. Number of moles of MnO4 negative in excess, it comes equal to 1 exponential minus 3 moles. So these were the total moles of MnO4 that were used. If this much reacted with iron plus 2, then how much will react with BaC2O4? We can subtract the total number of moles from this reacted moles. Now we can say number of moles of MnO4 negative that reacted with BaC2O4, it is equal to total number of moles minus moles reacted with iron 2 positive. Subtract these two, the values are 1 exponential minus 3 and we have 3.04 exponential minus 4. So number of moles of MnO4 reacted with BaC2O4, it comes equal to 6.96 exponential minus 4 moles. Now we have to find the ratio between C2O4 negative 2, which comes from BaC2O4 and MnO4 negative. Let's look into the question. They have given two equations. We are going to find out this ratio. So according to these two equations, in first equation 2 moles are lost, while in second equation 5 moles are gained. Now number of electrons gained and lost must be same, so we can multiply this equation with 5 to make it 10 electrons. We can multiply this equation with 2 to make it 10 electrons. So it will be 5 C2O4 negative, 10 CO2, 10 electrons. This one will be 2 MnO4 negative, 16 H positive, 10 electrons, 2 Mn2 positive, and 8 water. Now we just have to find the ratio between these two. One is C2O4 negative 2, this one. Second is MnO4 negative, this one. So the ratio is 5:2. So it is 5:2. Now number of moles of MnO4 negative, we already have calculated this. 6.96 exponential minus 4. So how much C2O4 will be reacting with this one? We can find moles of C2O4 negative 2 reacted. It's equal to multiplying these two dividing with this. So the answer is 1.74 exponential minus 3 moles. These are the moles of C2O4 negative 2 reacted. Now we can find the mass from these moles. So as mass is equal to moles into molecular mass, we already have the moles. We can find the molecular mass. It is given in question. It is 225.3. 1.74 exponential minus 3 into 225.3. It comes equal to 0.392 grams. Now this is the mass of BaC2O4 that reacted. So it means this is the pure mass, and the total mass given in question was 0.5 grams, which is of impure sample. Now we can find the percentage by mass. Percentage by mass, it is equal to mass of pure sample divided by mass of impure sample into 100. Putting the values, we have 0.392 divided by the given mass impure 0.500 into 100. So percentage by mass, it comes equal to 78.4%. Part D, barium hydroxide BaOH2 is completely dissociated in aqueous solution. Calculate pH of 0.120 mole per decimeter cube barium hydroxide at 298 Kelvin. Now we can write the equation for dissociation of barium hydroxide BaOH2. It dissociates into Ba2 positive and 2OH negative. Now in this one we have 2 moles of OH negative, so therefore we can multiply this concentration with 2. Now concentration of OH negative will be 2 into 0.120. So it is 0.240 mole per decimeter cube. Now we can find negative log. As we know that POH, it is equal to negative log of OH negative. Putting values, negative log of 0.240, POH comes equal to 0.6. Now as we know the formula, pH plus POH, it is always equal to 14. We have the value of POH 0.6, so pH is equal to 14 minus POH, or 14 minus 0.6. So the value of pH, it comes equal to 13.4. Question 3a part 1, define the term standard electrode potential. Now standard electrode potential is the potential of one cell compared to the standard hydrogen electrode, and the concentration should be standard 1 mole per decimeter cube, pressure should be 1 atmosphere, and temperature should be 298 Kelvin. So we can write the answer. It is the voltage of an electrode compared to standard hydrogen electrode and conditions are that concentration should be 1 mole per decimeter cube because it is standard electrode potential. Pressure should be 1 atmosphere. And temperature should be 298 Kelvin or 25 degrees centigrade. Three redox systems, we have A, B, C are shown. This is A, this is B, this is C. The ligand 1,2-diaminoethane. This one is represented by En in simplified form. Two electrochemical cells are set up to compare the standard electrode potential of three half cells. The diagram shows the relative potential of each electrode. Let's see the diagrams. These are the diagrams. Part 2, use this information to complete the table by adding the labels A, B, C to deduce the order of electrode potential for the three half cells. Let's first write the symbols for these half cells from this given table. We have RuEn3, 3 positive and 2 positive. RuEn3, 3 positive and 2 positive. This one is C. Then we have RuNH3, 6, 3 positive to 2 positive. 3 positive to 2 positive, this one is B. And this half cell is of RuH2O6 from 3 positive to 2 positive, and this is A. Again we have RuEn3, 3 positive to 2 positive, this one is C. Now from this we can see that B is negative and C is positive. So when comparing both of these, B is more negative than C. And when comparing A and C, we can see that C is negative while A is positive. So C is more negative than A. So we can say that B is more negative than C and C is more negative than A. So most negative will be B, least negative will be A, and in the middle we have C. Part 3, the complex RuEn3, 3 positive shows stereoisomerism. Ligand En is bidentate. Draw 3-dimensional diagrams, 3D diagrams to show two isomers of RuEn3, 3 positive. Represent the ligand En by using this. Name the type of stereoisomerism. Our first thing is that we have to find out that how many coordinate covalent bonds will be shown for isomer 1 and for isomer 2. Now we can see that in this they have given 3 En3 while 1 En is bidentate, so it makes 2 coordinate covalent bond. So 3 ethylene diamine, they will give 6 coordinate covalent bonds. Now we already have 2 lines, so we can draw 4 more. 1, 2, 3, 4. Similarly, in this one we have 1, 2, 3, 4, 5 and 6. So we can show 1 nitrogen, second nitrogen, then 1 nitrogen, second nitrogen, then 1 nitrogen and second nitrogen. All can be shown with this bond. We can do same for this one. 2 nitrogens, then 2 nitrogens, and then again 2 nitrogens. Now we can show the bonds. It should be mirror image, so it will be like this. Now both of these are mirror images of each other, so therefore the type of isomerism is optical isomerism. B part 1, an electrochemical cell consists of Br2 Br half cell and silver Ag half cell under standard conditions. Use the data booklet to calculate E naught of cell. Deduce the direction of electron flow in the wire through the voltmeter between these two half cells. We have to find out the E naught of cell in volts and direction of electron flow from which to which one. From data booklet we can find the values for this half cell and this half cell. We can write the reduction equation for both. First one is Br2, it gains electrons to form Br negative. And the voltage is 1.07 volts. For second reduction we have Ag positive, it gains electron to form Ag. The voltage associated with this one is 0.80 volts. Now for E naught cell we must use the formula. E naught cell is E reduction minus E oxidation. Now let's see which one will be reduction, which one is oxidation. So now from voltages we can find it out that more positive voltage means reduction, less positive voltage means oxidation. So this one is more positive, so this equation will move in forward direction or reduction direction, and this one will move in backward direction because it is less positive. Now putting values, E reduction is 1.07 volts minus E oxidation is 0.80 volts. So subtracting these two, the E naught of cell, it comes equal to 0.27 volts. Now second thing is the direction of electron flow. Let's see which electrode produces electrons and which electrode consumes electrons. Now as we can see that this electrode bromine, it gains electron or consumes electron, while this is oxidation, so it will lose electron. So Ag will produce electrons and electrons will move along the external circuit through voltmeter to Br. So we can say that electrons move from Ag positive Ag to Br to Br negative as given in the question. Part 2, water is added to Ag positive Ag half cell in B part 1. Suggest the effect of this addition on the E naught of cell. place a tick in the appropriate box and then explain your answer. Now we can see that the voltage, it depends on the concentration. Greater the concentration, greater will be the voltage, less the concentration, less will be the voltage. When water is added to this half cell, what will happen, that the concentration will decrease, so therefore voltage will also decrease. So if initially the voltage was 0.8, let's say now the voltage has dropped to 0.5 as the concentration has decreased. Now let's see what is the result for E0 of cell. Now we can subtract these two and value is 0.57. Now we can see that overall E0 of cell has increased from 0.27 to 0.57. So it will become more positive. And the explanation is that concentration of Ag decreases with dilution. So E0 for Ag positive, or this one Ag positive, Ag it will decrease or becomes less positive. And overall E0 of cell will increase. Part C, silver bromide AgBr, it dissolves in an aqueous solution of S2O3 negative 2 ions to form the complex ion. This one, the S2O3 negative 2 ions act as monodentate ligands. This is the equilibrium equation. Define the term ligand. Again the same thing, ligand is the species that makes coordinate covalent bond by sharing a lone pair. Of electrons, and it forms a coordinate covalent bond with central metal, which in this case is silver. Write an expression for the equilibrium constant for equilibrium 1. Now in equilibrium constant Kc, we have the concentration of products divided by the concentration of reactants. Now solid is not written because solid does not have any concentration. So we can write the products, which is Ag is 2O3, 2, charge is 3 negative, second is Br negative, divided by the concentration of reactants, we have S2O3, 2 negative, and the number of moles are also given, so the number of moles, it goes into the power, so it is power 2. Part 3, some additional data are given about the dissolution of AgBr in S2O3 negative 2. We have equilibrium constant Ksp of AgBr. Now Ksp is the solubility product, and this is for sparingly soluble salts. Sparingly soluble means that the solubility is very low. Now the numerical value is this. Then we have stability constant, K stability of this complex. So K stability is similar to Kc, but it is written for complex ions, 2.9 exponential 13. Use your answer to see part 2, this one, and these data to calculate Kc for equilibrium 1. Now in equilibrium 1, we can see we have both AgS2O3 negative, and we also have AgBr. because that is sparingly soluble. So we can find the value for Kc. Kc equals K stability value of complex into the Ksp of sparingly soluble salt, as both are present in the above equation, so we can multiply the values. We have 5.4 exponential minus 13 into 2.9 exponential 13. Now the value of Kc, it comes equal to 15.7. Let's find out the units by the help of C part 2. This one is power 1. This is the charge. This one is power 1. So we have mole per decimeter cube for first, mole per decimeter cube for second, divided by this one is squared, so we have mole per decimeter cube square. Now it will cancel out with the square, so therefore there is no unit that is left. Part D, the numerical values for stability constants, K stability of two other silver 1 complexes are given. This is for another with cyanide, this is for one with ammonia. We have the numerical values. An aqueous solution containing Ag positive is added to a solution containing equal concentrations of Cn negative, NH3 negative and S2O3 aqueous. The mixture is left to reach equilibrium. Then it says deduce the relative concentration of AgCN2, AgNH32, AgS2O32 present in the resulting mixture. Explain your answer. Now they have given the numerical values K stability for these. First one is AgCN2. For this the value is 5.3 exponential 18. Then we have AgNH32. For this one the value is 1.6 exponential 7. Third one AgS2O3, all 2, 3 negative. This is present here. The value of K stability is given. It is 2.9 exponential 13. Now greater the value of K stability, greater is the concentration. So we can say that K stability is directly proportional to concentration. So the one with the highest concentration will be written first. This one is power 18, so this is the one with the highest concentration, AgCN2 negative. Then we have this one at 13, this is second highest, so we can write AgS2O3 2 and it is 3 negative. And the lowest concentration will be this one, as it is the least value, so AgNH32 positive. And we can explain this that K stability is proportional to concentration. K stability for AgCN2 negative is highest, therefore its concentration will be high. And similarly for others, lower the value of K stability, less will be the concentration. Question number 4, part A, 1. Define the term lattice energy. Now lattice energy is the energy when 1 mole of ionic compound is formed from gaseous ions under standard conditions. We can write it. It is the energy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. Part 2, use the following data to calculate a value for the enthalpy change of solution of copper 2 chloride CuCl2. You might find it helpful to construct an energy cycle. They have given the enthalpy change of hydration of Cl negative, hydration of Cu2 positive, and lattice energy of CuCl2. Now we can draw the cycle. As they have given the hydration energy and lattice energy, so we can use this cycle. We have gaseous ions, and gaseous ions, they react together, they form ionic solid. So this is lattice energy. When ionic solid is dissolved, it forms aqueous solution. So we can say ions in solution. Ionic solid can be dissolved to form solution. Gaseous ions, they can also be dissolved to form ions in solution. Now the first one is lattice. Whenever 1 mole of ionic solid is dissolved in enough water to make very dilute solution, it is called enthalpy of solution. This is what we have to calculate. And from gaseous ions to ions in solution, they have given the values. Let's put the real ions. We have gaseous ions in copper chloride. We have Cu2 positive gas. Then we have 2Cl negative gas. It forms CuCl2, which is ionic solid, and it forms Cu2 positive aqueous and 2Cl negative aqueous. Now the equation is already balanced on all sides. First we can derive this formula. Let's give this one the value of delta H hydrations. Now in this one we have copper 2 positive. The value is minus 2099 for 1 mole. And then we have for chloride minus 378, as there are 2 mole involved, so 2 into minus 378. Adding them together, it gives the value of delta H hydration. Let's find the equation. This one is the common product, as both arrows are coming towards this one, and this is a starting point, so this is one step process and these two are two-step processes. So according to Hess's law, one step is equal to 2 steps. So we have delta H hydration. It is equal to delta H lattice plus delta H solution. We can find out the value of hydration by adding these two, or we can rearrange this equation. Delta H solution, it will be equal to delta H hydration minus delta H lattice. Putting values, this is delta H hydration minus 2099 plus 2 into minus 378 minus lattice energy. Lattice energy is given. Now calculating this one, the enthalpy of solution, it comes equal to minus 31 kilojoules per mole. Part 3, the enthalpy change of hydration of calcium 2 positive is this much. Use the data booklet to suggest why there is a big difference in the values of delta H hydration for calcium and copper. Now delta H hydration, it is always directly proportional to charge density of cation. Greater the charge density of ion, greater will be the enthalpy of hydration, because stronger forces of attraction will develop and more energy is released. Let's compare these two, calcium 2 positive and copper 2 positive. Both are present in period 4 of the periodic table. The atomic number of calcium is 20 while that of copper is 29. So as the number of shells remain same in period, but number of protons is increasing, so number of electrons is also increasing. So therefore along the periodic table size decreases. When charge is same and there is smaller size, it means charge density increases. So we can say that Cu2 positive is small as it has higher charge density. So it will attract water molecule more strongly because it is enthalpy of hydration. So in hydration water is involved. And stronger attraction means greater energy. So it will release greater energy. B part 1, identify the substances that are formed at anode and the cathode during electrolysis of saturated calcium chloride aqueous. We can see in calcium chloride aqueous we have Ca2 positive, we have Cl negative, we also have H positive as water is present, OH negative is also present. Now among the cations move towards cathode. H plus discharges more easily as compared to calcium 2 positive. So at cathode H plus it gains electron to form hydrogen gas. So at cathode hydrogen is formed. At anode we have these two ions. As it is saturated calcium chloride, so therefore chloride ion will be in more concentration as compared to hydroxide which are from water. So greater concentration can discharge, so Cl negative, it will lose electrons to form chlorine gas. So at anode we have chlorine Cl2. Part 2, calcium can be produced by an electrolysis of molten calcium chloride. Calculate the mass in grams of calcium formed when a current of 0.75 amperes passes through calcium chloride liquid for 60 minutes. Atomic mass is given. For this we can use the formula Q is equal to I into T, where Q is the charge in coulombs. I is the current in amperes. T is the time in seconds. Now it is the electrolysis of molten calcium chloride and they have asked about the mass in grams of calcium formed. In calcium chloride, Ca2 positive are present. It will gain 2 moles of electrons and will be deposited in the form of calcium. So as from this equation we can see that 2 moles of electrons are needed to deposit 1 mole of calcium. So 2 moles of electrons means 2 Faraday's charge. As the value of Faraday is 96,500 coulombs, so it will be 2 into 96,500 coulombs. And this comes equal to 1,93,000 coulombs per mole. So this charge is required to deposit 1 mole of calcium. So we can write moles of calcium against the charge. So 1 mole of calcium is formed from 193,000 charge. Let's look into the values given in the question. They have given 0.5 amperes. So we can use this current 0.75. Time is 60 minutes. So we can convert it into seconds by multiplying with 60. So Q, it comes equal to 2700 coulombs. Now if 1,93,000 coulombs, it forms 1 mole of calcium. So how many moles of calcium will be deposited with 2700 coulombs? We can cross multiply and find the value. It is equal to 0.0140 moles of calcium. Now we can find the mass by using the formula mass equal to moles into atomic mass. Atomic mass is already given, it is 40.1. Moles is calculated 0.0140 into 40.1. So mass of calcium, it comes equal to 0.56 grams. Question C, part 1. Explain what is meant by the term entropy of a system. Now entropy is disorderness, so we can write that it is the degree of disorder or randomness of a system. Greater the disorder, greater will be the entropy value. It says place one tick on each row of the table to show the sign of each entropy change. First one is sodium chloride dissolving in water. So as sodium chloride is dissolved from solid, it goes into aqueous form, so entropy is increasing. So when entropy is increased, it means delta S, which is entropy symbol, it is positive. Second is water solidifying into ice, so it means it goes from liquid to solid state. So as from liquid to solid, the disorder is decreased, so therefore delta S will be negative. Part 3. The evaporation of 1 mole of water has standard Gibbs free energy change delta G of 8.6 kilojoules at 25 degrees centigrade. Sketch a graph on the axis to show how delta G changes for this process between 25 degrees centigrade and 150 degrees centigrade at 101 kilopascals. This is the delta G value, positive or negative. This is temperature in degree centigrade. Now they have given the value of delta G at 25 degrees centigrade. This is 25 degrees centigrade and the value is 8.6 for evaporation of 1 mole of water. So we can put this value, as this is positive, we can put it anywhere here. So it is 8.6 kilojoules per mole. Now it says to sketch a graph and show delta G change for 25 to 150 degrees centigrade. Now what happens at 100 degrees centigrade for pure water, it changes from liquid state to gaseous states. And during this change, the temperature is constant, and as it is the phase change, all energy it is required to break the intermolecular forces. So therefore during phase change the value of delta G is always 0. Now we know that water boils at 100, so therefore at 100 it should be 0. Now we can draw a line to join these 2 points, and then we can extend up to 150 degrees centigrade. This is the line drawn. We can see it passes from 8.6 to 100 degrees centigrade and to 150 degrees centigrade. As we can see that the line moves downwards, so therefore overall Gibbs free energy it decreases as delta G is inversely proportional to spontaneity. So more spontaneous reactions mean less Gibbs free energy value. So at higher temperature, water evaporates by itself because temperature is more, so evaporation is faster, so therefore it will be more spontaneous, so less value of delta G is observed as we have seen in this diagram. Part D, the reaction between A and B is feasible at low temperatures but is not feasible at high temperatures. Deduce the signs of delta H and delta S for this reaction and explain why the feasibility changes with temperature. We have to find out the enthalpy change and we have to find out the entropy change for this reaction. Let's first find out the enthalpy change. Now it says the reaction is feasible at low temperature but not at high temperature. Now we know that enthalpy change can be for an endothermic reaction and for exothermic reaction. Endothermic reaction is feasible at high temperature because it needs more energy to go into the forward direction, but it is not feasible at low temperatures. So it means that this reaction is not endothermic, it must be exothermic. For exothermic reaction, at low temperature the reaction is feasible, it moves in the forward direction, but if the temperature is increased, what happens that the reaction moves in the backward direction. So therefore for this reaction the sign of enthalpy change is negative. And second thing is the entropy change. As we know that this reaction is giving out energy or releasing energy. So whenever something releases energy, it means its entropy is decreasing. For example, as we can see in the case from water gas to water liquid, when water gas it converts into water liquid, the disorder becomes less, so entropy will decrease. And this reaction is also exothermic in forward direction, so therefore in forward direction its entropy is decreasing. So sign of entropy change is negative. As this reaction is exothermic, so for exothermic we can say that the enthalpy change is negative, entropy change is also negative. So from Gibbs free energy delta G it is equal to del H minus temperature into delta S. This is negative for exothermic reaction. This is also negative. Now it says it is feasible at low temperatures. It means that at low temperatures delta G is negative. So when del G is negative, it means it is. Now it says at high temperature it becomes not feasible. It means when temperature is increased, this whole value T delta S, it will become more negative. So minus minus becomes positive and this whole value will become more positive as compared to delta H. So del G will become positive. At higher temperatures, del G becomes positive, so it is less feasible. So we can say that at higher temperature, delta H is less negative. This one is less negative because we are increasing the temperature, and this one will become more negative. as compared to T delta S. This one will be more negative than this. So when this more negative, it is multiplied with minus sign, it will become more positive. So overall delta G will become positive. Del G becomes positive. So when the value of del G is positive, it means that the reaction is not feasible. Question number 5, part A. Describe and explain the relative basicities of phenylamine, ethylamine and 4-nitrophenylamine. We have different amines. One is phenylamine. Phenyl means it is attached to benzene ring. Then we have ethylamine. And then we have 4-nitrophenylamine. This is first carbon, this is second, this is third and fourth. At fourth carbon, nitro group is attached. Now first thing is the basicity. Basicity, it depends on the presence of lone pair on nitrogen atom. Because this lone pair, it can accept a proton and this can behave as basic. Now more availability of lone pair means more basic and less availability of lone pair means less basic. So in first one we can see that in phenylamine, the lone pair of nitrogen, it delocalizes with the pi electron system of benzene ring. So this electron pair is less available for proton. In second one we can see we have alkyl group attached with NH2. Now alkyl group is electron donating as it has positive inductive effect. So due to positive inductive effect, it increases the chances of lone pair to be here. So therefore lone pair is more available for proton. So more availability of lone pair means more basic. In third one we can see that not only this lone pair is delocalized in the pi electron system of benzene, but also we have nitro group attached. Now in nitro group we have two electronegative oxygen atoms, so this lone pair will be further delocalized into NO2 system in the benzene ring. So we have least availability of lone pair in this one. So this is the least basic. So most basic is ethylamine, least basic is 4-nitrophenylamine, and in the middle we have phenylamine. Now we can use different points, as it is of 4 marks, we can use 4 points. First one is the basicity. Basicity is the availability of lone pair on nitrogen for donations. And most probably it is donated to proton or H positive. Second thing is we have ethylamine. So we can say that ethyl group is electron donating in nature, or you can say it has more positive inductive effect. So lone pair on nitrogen is more available. And it can easily accept a proton. Then we have phenylamine. We can say in phenylamine lone pair on nitrogen is less available, as it is delocalized into the pi electron system of benzene. And then we have this nitro group. For this one we can say that in 4-nitrophenylamine we have nitro group which is electron withdrawing, so lone pair on this nitrogen is least available. To accept a proton. That's why ethylamine is most basic and 4-nitrophenylamine is least basic. Part B, the di R, it can be synthesized from 4-nitrophenylamine in 2 steps. This is R, this is azodi. We have nitro group and amine group in the reactant, and in the product we have nitro group, nitrogen bridge, and also this thing is present which is called naphthol. Part 1, deduce and draw the structure of organic salt Q in the box. Second is to suggest reagents and conditions for step 1 and step 2 in B. Now to form this nitrogen bridge of azodi, what we can do is that we can first convert this into diazonium salt. And then we can react it with this reactant and it will be converted into this R. So step 1 is diazotization. And we need HNO2 along with HCl. So this one will be converted into NO2 positive, benzene ring, and we have nitrogen bridge. There is positive charge on this nitrogen and also due to HCl, Cl negative is present. Now this is the diazonium salt. Along with the formation of water molecules. In second step now we can attach this diazonium salt into one naphthol. We have OH, 2 benzene rings present. Now OH is 2,4 directing, so this is second position and this is fourth position. As we can see that this group is attached on second carbon. So now what will happen, that benzene it will attack this nitrogen and it will be attached to second position. The reaction is called electrophilic substitution, and one hydrogen it is replaced with this whole group. So we have already drawn the structure. We can write the reagent and conditions. In step 1 we have used NaNO2, HCl aqueous, and the temperature must be less than 10 degrees centigrade because this diazonium ion it is very unstable and it can decompose easily to form nitrogen gas and nitromethane. In second step we have used 1-naphthol and alkaline conditions. Now this HCl and this NaNO2 they will both react together to form HNO2 along with sodium chloride, and this HNO2 is then used in this reaction. Part C, compound G can be synthesized from methyl benzene in 3 steps. We have methyl benzene, this is step 1, it forms E, then in step 2 it forms F, which in step 3 forms this carboxylic acid, nitro group and bromine. So give the systematic name of compound G. Let's first find out the name of this compound. You can see we have bromine, we have NO2, we also have carboxylic acid group. So when carboxylic acid group is present with benzene, it is called benzoic acid, and we can position NO2 and Br. So this will be first carbon, this will be second, third and fourth. So we have 4 bromo, 2 nitro, benzoic acid. Or you can also say, instead of benzoic acid, you can say benzene carboxylic acid. Part 2, deduce the identities of E and F and draw their structures in the boxes, and also suggest reagents and conditions for 3 steps. As we can see that this side chain CH3, it has converted into carboxylic acid group, so it is the oxidation of side chain in benzene. We also have addition of NO2 group and Br group into the benzene ring. So as methyl group is 2,4 directing in nature, so incoming electrophile it will be either added to second position or fourth position. Now we can see it is on second position and this one is at fourth position. So first we can add NO2, or you can also add Br2 first. So for addition of NO2 the process is called nitration. And for nitration, we need concentrated sulfuric acid along with concentrated nitric acid. Both will react together and form NO2 positive along with HSO4 negative and H3O positive. This will be used as electrophile and it will be added to benzene ring. Now we have added NO2. In second step, we can add Br, this one. So it will be added through the process called bromination. But first we have to generate an electrophile of Br. So it can be done if we use bromine along with AlBr3. What will happen that this aluminum, it will make another bond with this bromine, and Br positive will be generated along with AlBr4 negative. And this one can act as electrophile, which will be added to benzene ring. So now the position from respect to CH3, one was 2 position and then we had 4th position, so it can add to this position. We already have CH3, we have NO2. Now new entry is Br. Now in step 3 we can oxidize this side chain by oxidizing agent. So we can use hot acidified MnO4 negative, which is oxidizing agent, and it will convert this methyl into carboxylic acid group. Question 6 part A. There are 4 possible structural isomers of C8H10 that contain a benzene ring. Now in benzene we have 6 carbon atoms and 2 extra carbon atoms are present in this structure. Draw the skeletal formula of the 4 structural isomers in the appropriate boxes. The number of peaks observed in carbon-13 NMR spectrum of each compound is given. We can see in isomer 1, 2 we have 3 peaks and then 4 peaks. Then in isomer 3 and 4 we have 5 peaks and 6 peaks. Let's draw the structure of this given compound. We have C8H10. We have benzene ring. Now benzene ring is C6H6. We need 2 more carbon atoms, so we can add 2 methyl groups. Let's suppose one is this one is this one. Now 2 hydrogen are removed and 2 CH3 are added, so we have C8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. So this is the possible structure. Now the position of CH3, it can change. This is first position, this is second position. We can also add to 1, 3 positions. So it will be like this. This is first position, this is second, this is third. 1, 3 dimethyl benzene. Or we can add to 1 and 4th positions. One 4 dimethyl benzene. We cannot add to this position because it will again become 1, 3 and this position will become 1, 2. Now second possibility is that you can add ethyl group instead of methyl group. So if we add ethyl group CH2, CH3 with benzene ring, its position will always be 1. So we have 4 different possibilities. Let's see which one will give how many carbon-13 NMR peaks. Now in the first structure we can see that this CH3 is identical to this CH3 as both are attached to the carbon atom of benzene ring having no hydrogen atom. So we have 1 peak. Then we can see that this carbon and this carbon are exactly similar because both carbon does not have any hydrogen atom and both carbons are attached to CH3. So this is second peak. Then we can see that this carbon and this carbon are identical as both are same distance away from these carbon atoms. So this will give peak 3 and these two at the last they will give peak 4. So this structure will give 4 peaks in carbon-13 NMR spectrum. So we can write we have to draw the skeletal formula, so we are not going to use CH3. We can just draw the lines. This is one CH3, this is second CH3. Let's move towards second one. We have CH3 and CH3, both are similar, so they will give one peak. Then we can see this carbon is exactly similar to this carbon, as both have no hydrogen atom and both are attached to CH3. So this will give second peak. This carbon is alone, it will give third peak. These two are symmetrical, they will give fourth peak, and this alone will give fifth peak. So we have 5 peaks for this second structure. So we can draw it in isomer 3 as there are 5 peaks involved. This is benzene ring and we have CH3 on first carbon atom and CH3 on third carbon. Now in the third one, this CH3 and this CH3 similar, so first peak. This carbon atom similar to this one, second peak. Now we can see that this carbon CH, this carbon CH, they are both symmetrical as both are attached to carbon atom having no hydrogen atoms. Similarly, this carbon and this carbon are also same. So all these 4 carbons are similar, so they will give just one peak, which is the third one. So we have 3 peaks for this structure. The position of methyl group is opposite, so we have 1 and 4th position. Now in this one we can see we have CH3, first peak, then this carbon is bonded to 2 hydrogen atoms, so another peak. This one having no hydrogen atoms, so third peak. These two are exactly similar, fourth peak. These two are also symmetrical, fifth peak, and this one is alone, sixth peak. So we have 6 peaks in this structure. We can draw this one. We have benzene ring and ethyl group is present, so we can draw it like this. Part B, a 3-step synthesis of X. We have C10H10O from benzene is suggested as shown. This is benzene ring. We have this reactant in the presence of AlCl3 and step 1. Then in step 2, it is converted into acyl chloride. And in step 3, we use aluminum chloride and see what product is formed. Now it says step 1 is the alkylation of benzene by electrophilic substitution. Use RCl to represent this structure. Write an equation for the formation of an electrophile from RCl and AlCl3. Now what happens that aluminium, it makes a coordinate covalent bond with chlorine and it will become AlCl4 negative, and we have positive R group which behaves as an electrophile. So we can use these to write the equation. RCl plus AlCl3, the product will be AlCl4 along with R positive. Part 2, deduce and draw the structures of W and X in the boxes, and then we have to suggest the reagents and conditions for step 2. In step 1, we have AlCl3 and this compound. This chlorine will be attached to AlCl3 to form AlCl4 negative. And this rest of the part, it becomes positive. We have 3CH2 and COOH. And this will become positive. Now benzene can attack this carbon atom and it will make a bond. Along with electrophilic substitution, one hydrogen is replaced. We have benzene ring. CH2, 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 COOH. Now this is the first structure of W that is formed. We can also draw skeletal structure instead of this one. It will be benzene. Then we have 1, 2, 3, 4 carbon atoms. 1, 2, 3, 4 carbon atoms along with double bond oxygen and OH. Now in second step we can see that carboxylic acid, it is converted into acyl group. So to convert carboxylic acid into acyl group, we can use SOCl2 or we can use PCl5 or PCl3 in the presence of heat. So for step 2 we can write the conditions. You can write any one. Let's draw X. Acyl chloride, it reacts with AlCl3 to form this structure. Now again this is similar. AlCl3, it first makes a bond with Cl to make AlCl4 and this carbon will become positive. Then benzene, it can attack this carbon atom to form the product. As alkyl groups are attached and alkyl group have positive inductive effect and they are 2,4 directing, so incoming electrophile, it can be added to second carbon or fourth carbon. We can add it to second carbon. So the structure will be like this. We have benzene, one, two, three, and then we have 4, 5, 4, 5, and as this is positive, double bonded to oxygen. Now it will make a new bond with benzene. Now we can find the molecular formula. We have 1, 2, 3, 4, 5, 6 carbon atoms in benzene ring, 7, 8, 9, 10, 4 carbon atoms in this one. Then we have 1, 2, 3, 4 hydrogen in benzene ring and 2, 4, 6 hydrogen here. 2, 6 and 4 becomes 10. So yes, it is similar and 1 oxygen is also present. So this is the structure of step 3. Part 4. Complete the mechanism for the reaction of benzene with electrophile formed in B part 1. Include all relevant charges and curly arrows showing the movement of electron pairs and draw the structure of the intermediate. Now we had R group. In first step, first we can use this arrow as the electrons of benzene, they are donated to this R group. Now what happens is that now R will make a bond with benzene ring. We can show it to this carbon atom. So with this carbon, R group is attached. Also in benzene ring, each carbon atom is bonded to a hydrogen, so we can show this hydrogen. Now this carbon is making 4 sigma bonds, so therefore pi electrons are lost. Rest of the 5 carbon atoms, they still have pi electrons, so therefore we have partial ring structure. And this positive charge is now on benzene ring. So what will happen that this electrons, they will go back into the benzene ring and this hydrogen, it will be removed in the form of a proton. Question number 7, part A. In aqueous solution, chlorine dioxide ClO2 reacts with hydroxide ions as shown. This is the reaction and these are the products. A series of experiments is carried out using different concentrations of ClO2 and OH negative. The table shows the results obtained. This is the concentration and this is the rate in mole per decimeter cube per minute. Explain the term order of reaction. Now, order of reaction is the power to which a concentration of reactant is raised in the rate equation. So we can write the power to which concentration of reactant is raised in the rate equation. Part 2, it says use the data in the table to determine the order of reaction with respect to each reactant. We have two reactants, ClO2 and OH negative, and then explain your reasoning. Now in the table we can see that the concentration of first reactant is similar in first and second experiment, so we can use this to find out the rate of reaction for second. As we can see, this one has increased 4 times. 0.3 into 4 is 0.120, and the rate of reaction, let's divide these two, so it also comes equal to 4 times. It means if this reactant is doubled, the rate of reaction also doubles. So this is first order with respect to OH negative. Now we can see that this concentration and this one is similar, so we can use this to find out the order of reaction for first reactant. So from 0.20 to 0.50, the increase is 2.5 times. Now let's see how much difference is between the initial rates. So if we divide these two, we get 6.25. Now in this one we have increased the reactant 2.5 times, so 2.5 when squared it forms 6.25. So it is second order reaction with respect to this reactant. Now we can explain it. First we can use experiment 1 and 3. We can say ClO2, it is increased 2.5 times. So rate of reaction increases by 6.25. So as we are doubling the concentration, the rate of reaction is increasing by 4 times. So therefore we can say that this is second order. Now for second one, we can compare experiment 1 and 2. OH negative is increased 4 times. Rate also increases 4 times. So this is first order. Now it says use your answer to A part 2 to construct the rate equation for this reaction. We can write the rate equation. Rate is equal to constant K into the concentration of first reactant, which is ClO2, into the concentration of second reactant, as both are part of rate equation because both affect the rate of reaction. Now OH negative is first order, so it is raised to the power 1, which is not needed to write. And ClO2 is second order reactant, so therefore it is going to be powered 2. Use your rate equation and the data from experiment 1 to calculate the rate constant K for this reaction. Include the units of K. We have to find out the value and units of K. Going back to the table, we can see that for first experiment, this is the concentration of ClO2, this is the concentration of OH negative, and this is the initial rate, and these are the units for initial rate. We can use these values. So rate is 7.20, exponential minus 4, and unit is mole per decimeter cube per minute. Concentration of first reactant, which is ClO2, in the table it is given as 0.020 mole per decimeter cube. Concentration of second reactant is 0.030 mole per decimeter cube. Let's use this formula to find the value of K. We have rate is equal to K into first reactant power 2 into concentration of second reactant. For K will be equal to rate of reaction divided by concentration of ClO2 raised to power 2 and OH negative. Now putting these values, K will be equal to 7.20 exponential minus 4 divided by 0.020 power 2 into 0.030. Now we can calculate the value of K. It comes equal to 60. Let's find out the units. We have on the top we have mole per decimeter cube per minute. On the bottom we have mole decimeter cubes. As it is squared, so it will become mole square decimeter minus 6. This one will remain same, mole per decimeter cube. Now this can cancel out with this one. We have this as left, so it is per minute, and we have per mole square, and decimeter minus 6 will become dm plus 6. Part B, the decomposition of benzene diazonium ions C6H5N2 positive using a large excess of water is a first order reaction. The graph shows the results obtained. In the graph we can see on y-axis we have C6H5N2 positive in mole per decimeter cube. On y-axis we have time in seconds. Number 1. Draw the structure of organic product formed in this reaction. Now they have given benzene diazonium ion, which is C6H5N2 positive. It can be written as like this. We have N2 and it is positive. So now when hydrolyzed in the presence of water and warmed at above 60 degrees centigrade, it converts into phenol, and nitrogen gas is released. As this is unstable, plus H positive ions is also formed. So the structure of organic product is this one. We have phenol that is formed. Part 2, use the graph to determine the rate of reaction at 100 seconds. Show your working. Rate is in mole per decimeter cube per second. Let's see in the graph. This is the value at 100 seconds. Let's draw a tangent. Then we can find the change in concentration and change in time and divide both to find out the rate of reaction. This is the tangent drawn at this point. Now we have two values. One is at 0.0175 concentration. The second is at about 290 seconds. Now we can divide both to find out the rate of reaction. As rate, it is equal to change in concentration divided by time taken. So change in concentration is 0.0175 minus 0. So it is equal to 0.0175, and time taken is about 290 seconds. So the value obtained for rate is 6 exponential minus 5 mole per decimeter cube per second. Part C, sketch a concentration time graph for zero order reaction. Use your graph to suggest how successive half-lives for a zero order reaction vary as the concentration of reactant decreases. Indicate this by placing tick in the appropriate box in the table. We have concentration, we have time, and we have to find out whether successive half-life it decreases, there is no change, or whether it increases. So if it is a zero order reaction, in zero order reaction means that the successive half-life will always decrease because time decreases. For zero order, concentration has no effect on rate of reaction and half-life decreases with time. For first order reaction, half-life is constant. For second order reaction, half-life will increase. Now let's suppose if this is the concentration of 100. This is the line for first order reaction. Now we can use the concentration. If this is 50, this is half of 50, which is 25. This will be half of 25, which will be 12.5. Now we can measure the successive time. We can see that in this one, we have this much time that is used in the first half when 100 becomes 50. Then when 50 becomes 25, the time has decreased. And then when 25 becomes 12.5, the time has further decreased. So we can see there is decrease in time. So half-life decreases. Question 8, Part A, state and explain the relative rate of hydrolysis of acyl chlorides, alkyl chlorides and aryl chlorides. Let's draw the structures. First one is acyl chloride. Let's draw the structure CH3, CH2. Then we have C double bond O, Cl. This is acyl chloride. Second is alkyl chloride. In alkyl chloride, carbonyl carbon is not present, so we can write CH3, CH2, Cl. Third one is aryl chloride. In aryl chloride, benzene ring is present. Cl. Now we have to find out the hydrolysis. In hydrolysis, what happens that carbon-chlorine bond it breaks and this part becomes carboxylic acid while this part becomes HCl. Similarly, in this one, carbon-chlorine bond will break and we have alcohol plus HCl. In benzene chloride, the carbon-chlorine bond will break and phenol along with HCl is formed on hydrolysis. Now ease of hydrolysis depends on the weak bond. So weak bond means faster hydrolysis. And this bond is between carbon and chlorine. So weakest bond between carbon and chlorine in these three will give the fastest rate of hydrolysis. So in these three, in first one we can see that this carbon it is also attached to electronegative oxygen atom. So what will happen that this carbon will become electron deficient. So when it becomes electron deficient, this bond is easy to break. In second one we can see that alkyl group is electron donating in nature, so it donates its electrons to this bond, so therefore this bond becomes stronger. In third one we have benzene along with chlorine, so the lone pairs on chlorine they get delocalized into the benzene pi electron system, and due to that this bond becomes more stronger. So the strongest bond is the slowest, so we have aryl chloride which is slowest. Then the fastest rate will be observed from this acyl chloride, and alkyl chloride is in between. We can write the reasons. First for acyl chloride. Carbon in CCl bond in acyl chloride it is also bonded to electronegative oxygen atom. Which makes it electron deficient. So we can say that CCl bond is weakest. Second thing is for alkyl chlorides. In alkyl chlorides, carbon-chlorine bond is strengthened due to positive inductive effect of alkyl groups. So therefore CCl bond is stronger comparatively. In third one we have aryl chlorides. Now in aryl chloride, the lone pair on chlorine is a part of delocalized electron system. So it will give a partial double bond character due to which CCl bond is strongest. The strongest bond it gives slowest rate and the weakest bond it gives fastest rate. Part B, the drug remifentanil is shown. This is the drug. It is a structure. Remifentanil is completely hydrolyzed under acidic conditions. 3 different organic products are formed. Draw the structures for these organic compounds in the boxes. So we have to find out the 3 products. Let's first find the functional groups or the linkages present. We have this ester linkage. This one is also ester linkage RC double bond OR. This one is amide linkage RC double bond ON. So for ester linkage we know that when it is completely hydrolyzed it forms carboxylic acid and alcohol. The carbonyl part forms carboxylic acid while the oxygen part it forms alcohol. For amide we have RC double bond ON. This bond breaks and this converts into carboxylic acid and this one converts into amine. So carbonyl carbon becomes carboxylic acid and second one will become amine. So we can break this after hydrolysis. This bond will break. This part it goes into alcohol. This part will become carboxylic acid. Again we have ester. This will break and it will form alcohol. Now these both are 1 carbon alcohol, so therefore they are similar. This part will become carboxylic acid. Then we have amide bond. This is broken. This part will form carboxylic acid. So in the center, this whole part, it will give one structure. And then we have carboxylic acid and then we have alcohols. So we can draw all these three. Let's first draw the big one. We have carboxylic acid. 1, 2, 3 and then nitrogen. 1, 2, 3 and then nitrogen. Nitrogen divides into 2. Then we have this carbon. Then second nitrogen, which is attached to benzene ring. And this carbon, which will form carboxylic acid. So this is the first structure. Second structure is of 1 carbon alcohol. And this is the third structure. We have 1, 2, 3 carbon carboxylic acid that is formed. So 1, 2, 3. Now amide is changed into amine and hydrogen atom is attached. As this nitrogen, it was making 3 bonds, now it is making 2 bonds, so we also have 1 hydrogen that is attached. Part C, compound Y, we have C5H10O2. It reacts with sodium carbonate aqueous to evolve bubbles of gas. The proton NMR spectrum of compound Y in deuterium oxide is shown. This is the NMR spectrum. Use this information to suggest a structure for Y. Now first thing that they have given is that this compound, it reacts with carbonate to form gas. As we have 2 oxygen atoms, so we can assume that this compound is organic in nature and therefore it could be carboxylic acid. Let's draw carboxylic acid of 5 carbons and find its molecular formula. We have CH3, CH2, 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 COOH. So now we have 5 carbons, 10 hydrogens and 2 oxygens. This is similar to this one and it will form CO2 gas when reacted with carbonate, because acid plus carbonate gives salt, water and carbon dioxide. Let's find out the proton NMR spectrum of this compound Y. First we have to find out different environments. Let's first draw this structure. 1, 2, 3, 4. Then we have this. Now let's draw the hydrogen atoms. These 3 hydrogen atoms are present with 1 carbon. These 2 hydrogen atoms are present with this carbon. Then we have these 2 hydrogens. Then these 2 hydrogens. Now let's find out the environments that will give peaks. These 3 are identical, so one environment. These 2 are identical, so second environment. Then we have third. Then we have fourth. So 4 environments are there. As this hydrogen, it is exchanged with deuterium because D2O is present. So we have 4 environments. So 4 peaks should be there, but only 3 peaks are given, 1, 2 and 3. Now it means that this structure is incorrect. We can draw another branch structure in which we can branch one of the carbon atoms. For example, we have 1, 2, 3, then COOH, and we can branch one carbon over here. We can draw hydrogen atoms. 3 hydrogens are present with this carbon, 3 hydrogens are present with this carbon, 1 hydrogen is present with this carbon, 2 hydrogens are present with this carbon. This is exchanged with deuterium. Now for environments, we can see that these two protons system, they are present in the same environment because both CH3 are attached to CH. This is the second environment, this is the third environment. So 3 peaks can be observed. As we have 3 peaks, so this is the possible structure. Now let's find out the splitting pattern by using n+1 rule, where n is the number of neighboring hydrogen atoms. Now let's look into this structure. First one is this. We have CH2, the neighbor hydrogen is just 1. So 1 plus 1 will become 2. There will be a splitting pattern of 2 for this CH2. Then second one is this one. On the neighbor, we can see we have 3 and 3, 6 protons on one side and 2 protons on another side. So in total we have 8 protons. So n is 8 plus 1, it will become 9. So we can see a multiplet. So this peak is due to this proton, CH proton. Now third one is this CH3. On the neighbor, we can see we only have one CH, one hydrogen is available, so n is 1. For CH3, which are 2 in number, we have one neighbor plus 1, it will give duplet. So these two are duplets. As we can see that this CH2, it is nearest to oxygen atoms which are electronegative, so de-shielding will take place and we have more value for chemical shift in ppm. So this peak, it is because of this CH2, and this third peak, it is because of these CH3 groups. Now we can draw the structure for Y. We have 2 alkyl groups which are attached to this carbon. Then we have CH2, then we have C double bond O, OH. Now it says use the data booklet, the proton NMR spectrum and your answer to C part 1 to complete the table. Now we have to find out the environment of protons, splitting pattern and number of hydrogen atoms responsible for the peak. The first one is the chemical shift 0.95. Then we have 1.90, then 2.20. We know the environment of proton. This is at 0.95, so it is due to alkyl groups CH3. So we can write CH3. Then second one is 1.90. This is because of CH, this one. And third one is because of CH2. So we have CH and then CH2. Now splitting pattern. Splitting pattern is, we have 2 peaks, so this is duplet. We have more than 6 peaks, so this is multiplet. Again we have 2 peaks, so this is duplet. So we have duplet, multiplet, and again duplet. Now number of protons responsible for the peak, as we can see we have 2 CH3 groups that was present in the first environment. So we have 6 protons, one is this one is this one, so 3 and 3 become 6. 6 protons. Then in multiplet only 1 proton is present, and in CH2 group only 2 protons are present. 6, 1 and 2. Thanks for watching. If this was useful, please do like, subscribe and share.